Algebra 1, that would be Spanish for hello. Oops. So the opening exercise is really a great review of what we've been doing the past few lessons. So I would make sure you take good notes, and so you remember all the stuff that we've been doing, and you can ask questions if there's something you really don't understand. So we're going to begin with fill in the blanks of the table with the appropriate heading or descriptive information. We have a function f of x, and the graph is always y equals f of x. So here, if we have y equals f of x plus k, we're translating. When k is greater than 0, we're going to translate up. When k is less than 0, we're going to translate down. That's vertically. And then horizontally, our graph looks like y equals f of x minus k. So when k is greater than 0, we translate right. When k is less than 0, we translate, left. Now notice, let me write it down here, this is f x minus k. I'm just looking at k there, noticing that there's a minus sign here. So I'm just, if there's a minus sign there and I look at k, when k is greater than 0, I go right. When k is less than 0, I go left. Continuing on the vertical side, this is vertical, that's horizontal. We have our scale factors. Scale factor k. So in this spot, I'm going to write, it's going to be easier to write sideways, y equals k f of x. It's on the outside of the function. That's how we know it's vertical. When k is greater than 1, we are doing a vertical stretch by a factor of k. It's a vertical stretch by a factor of k. When k is between 0 and 1, that means that it's a fraction. We do a vertical shrink by a factor of k. When k is between -1 and 0, that means it's a negative fraction. We do a vertical shrink by a factor of k and a reflection over the x-axis. And then when k is less than -1, we do a vertical stretch by a factor of k and reflect it over the x-axis. Now here we see that y equals f of 1 over k x. So when your factor is on the inside of your function, that's the horizontal one, which is harder. We have to do a little bit of work with that one to get our information. All right, so when k, just this part, when k is greater than 0, we have a horizontal stretch by a factor of k. When k is a fraction, that means that we would have 1 over k, which is just plain old k. We have a horizontal shrink by a factor of k. Now, when we have a negative fraction, when we have a negative fraction, we have another horizontal shrink and a reflection across the y-axis. And here we have a horizontal stretch and a reflection over the y-axis. Okay, it's a really good summary of everything that we've learned the past 3 lessons. So Exploratory Challenge 1, a transformation of the absolute value function f of x equals absolute value x minus 3 is rewritten here as a piecewise function. describe in words how to graph this piecewise function. So these are two lines. First, I would graph the line y equals negative x plus 3 for x values less than 3. Then I would graph the line y equals x minus 3 for x values greater than or equal to 3. So describe how to graph the following piecewise function, then graph y equals f of x below. So I have three piecewise functions here. The function of f can be graphed of the line y equals negative 3x minus 3. Let's do that one in blue. When x is less than or equal to negative 2. So 3x minus 3. I know that's going to cross my y-axis at negative 3. And I have a slope of negative 3 over 1. So I'm graphing negative, y equals negative 3x minus 3. So I'm going to go up 3 and left 1. 1, 2, 3, 1. 1, 2, 1, 2, 3, 1. 1, 2, 3, 1. 1, 2, 3, 1. But if I look at that domain, this is only for x values less than negative 2. So really, I can only graph from that point. I have to erase those. Next, I can graph y equals 0.5x plus 4 for the domain of negative 2 to 2. So this crosses the y-axis at 4. 1, 2, 3, 4. And my slope is 0.5, which is 1/2. So I'm going to go up 1 over 2, up 1 over 2, up 1 over 2. And my domain, let's see, I go down 1 over 2, down 1 over 2. My domain is negative 2 to 2. So really, I can only use those values of x. So it would be right from there to there. And I'm actually going to erase all of those dots. Let's use green for the last one. Y equals negative 2x plus 9. I cross the y-axis at 9. And I'm going to go negative 2, negative 1. Negative 2, negative 1. That's not right. 2 over 1. Oh, I didn't see that. That's a negative 2. Sweet, because there's no way that was going to work. So we're crossing at 9. I'm going negative 2, positive 1. And what is my domain here? X is greater than 2. So that would be this way. And erase those dots. So I just graphed the piecewise function. And the description was what you heard me do verbally. I know, hear me talking so much. All right, using the graph of f below, write a formula for f as a piecewise function. To get that piecewise function, I really need to discuss my domain first. So I'm going to piece these out from here to here. I know that negative 7 is going to be less than or equal to x, less than negative 4 for that section. And I have this section right here, negative 4 less than or equal to x less than 1. This section right here, is 1 less than or equal to x less than 4, and then from there to there, 4 less than or equal to x less than or equal to 7. Notice my signs. This is just less than, that's less than or equal to. That equal to part can't be on both spots because the -4 can't be included in both line segments. Here I have no equality, equality, none, yes. Okay, they just can't be in the same places. So let's go ahead and try to write our piecewise function. Just like before, I do f of x equals and then a big bracket. So this first line right here, let's do that in red. That first line right there, if I continue it up, it looks like it's crossing the y-axis at 0.5. So that's my y-intercept, -0.5, and my slope is up 1 over 2. So rise over run. I have 1/2 x minus 0.5 with a domain of -7 less than or equal to x less than or equal to, that's a 3. You guys probably knew that and didn't say anything. You have to tell me when I make mistakes. Okay, the next line segment we're going to do in blue. It's right there. And that is a simple f of x equals -2 with a domain of 3 less than x less than 1. And it looks like I changed. Here I have an equal sign and there I do not, which is great. Okay, it just can't be in both places. The next segment, let's do that in green. Just working on this one right here. If I continue that down a little bit, let me see. Looks like a slope of 1. Looks like it crosses the y-axis at 1, 2, 3. And the slope is -1, -1. So 1x minus 3 with a domain of 1 less than or equal to x less than 4. And the last but not least is, let's do purple. Right there. I'm not sure where that crosses the axis, so I'm going to sketch it up so I can see it. Looks like it crosses right at 5, and it has a slope of up 1, -1, so -1x plus 5 with a domain between 4 and 7. That was tough. Not hard, but it was a lot of work, wasn't it? So the graph of y equals f of x of a piecewise function is shown. The domain of f is -5 to +5, and the range is -1 to 3. Range is always our output, so it's the y values. So the range goes from -1 up to 3. Because if we look over here, that's where we start, and we look over here, that's where we end, or the other way around. The domain is always this direction, the input. It goes from -5 to 5. Mark and identify 4 strategic points helpful in sketching the graph of y equals f of x. Let's see. I need that point, that point, that point, and that point. So I would just say -5, -1, -1, 1, 3, 1, and 5, 3. Alright, sketch the graph of y equals 2 times f of x and state the domain and range of the transformed function. How can you use part A to help you sketch the graph of y equals 2 times f of x? First of all, our domain is not going to change. it's still -5 to 5. Our range is going to change. So let's look at that. For every point x, y, x, y on the graph, of y equals f of x, there is a point x, 2y. That's a vertical stretch. I can change my y value to 2 times my y value on the graph of y equals 2 times f of x. So I can actually just find the 4 strategic points, 1, 2, 3, 4, and just do the math with that. Okay, these are the points that we found in the last slide. I have, -5, -1 becomes -5, -2. Let's go ahead and do that in red. -5, -2, all blue. Becomes this one. Okay, next let's do, -1, 1. That becomes -1, 2 because of what we're doing here. So that one was in red. Let's do one in blue. -1 up 2. Okay, next one. I have 1, 2, 3, 1. Gosh darn it. Over 3 up 1 becomes over 3 up 2 because of this. So that would be in red. And this one is in blue. 3, 2 over 3 up 2. And that last strategic point, it's really the easiest way to do this, is over 5 up 3. Let's do it up here. 5, 3 becomes 5, 6. So this one is graphed in red. Let's graph that one in blue. Over 5 up. 1, 2, 3, 4, 5, 6. And then we can connect the dots, which is going to be hard, but I can do it. And that is our new line. Phew! I forgot to do the range. So for this one, our range, because we're affecting our y values, the original range was -1 to 3, so I'm going to multiply that by 2. -2 to 6. Okay, this value right here, I multiplied by 2 from the original. Just noticed a mistake, so I'm going to change it in bright purple. That's a y. Alrighty. Right here I have a horizontal scaling with a scale factor of 1/2. And the graph y equals f of x, which I've drawn there, is the graph of y equals f of 2x. Sketch the graph and state the domain and range. How can you use the points identified in part A, those significant points, to help sketch y equals f of 2x? So here our domain is changed. On part B, the range was changed because it was vertical. Here the domain is changed, oh my goodness, because it's horizontal. So we're going to multiply our domain by that scale factor. And it becomes, instead of -5 to 5, it's going to be -2.5 to 2.5. and our range shouldn't actually change any. -1 to 3. I just realized a mistake on the last slide. Hold on. All right, so we have our domain and range, and now we're going to talk about those significant points. For every point on the graph, y equals f of x, there is a point x over 2, y, on the graph of y equals f of 2x. So for this first point, I'm at -5, -1. So if I graph a new point, it's going to be x over 2, so -5/2, -1. So if I graph that one with purple, it's going to be -5/2, -1. So that would be 2.5, -1, about right there. The next significant point is over 1 up 1. It's now -1/2 up 1. I'm going to graph that in purple. -1/2 up 1, about right there. The next significant point was over 3 up 1. It's now going to be 3/2 up 1, or 1.5. Graph that in purple. So 1.5 up 1, right about there. 1.5 up 1, yep. And that last significant point is over 5 up 3. It's now going to be 5/2 up 3, or 2.5. So 1, 2.5 up 1, 2, 3. And now we would connect those dots. A little bit harder. Oops, I don't like that. A little messy. On your paper, it's going to look awesome though, right? Okay, last slide. I know this is a tad bit long. How does the range of f in Exploratory Challenge 2 compare to the range of the transform function g, where g of x equals k times f of x when k is greater than 1? We have, for every point, I keep using that highlighter pen, for every point xy, sorry, my sleeve just got caught in everything. So for every point xy, in the graph of y equals f of x, there is a point x ky in the graph y equals k f of x. Okay? When k is greater than 1, we have a vertical scale, vertical stretch. And when k is between 0 and 1, we have a vertical shrink. How does the domain of f in the Exploratory Challenge 2 compare to the domain? For every point xy in the graph y equals f of x, there is a point kxy in the graph of y equals f of 1 over kx. So that's for values between 0 and 1. We have a horizontal, so for those values I have a horizontal scaling, horizontal shrink. Can't spell shrink. tip, I have a horizontal shrink. So my domain, if my domain for that original one was between -5 and 5, sorry, my domain becomes -k5 to k5. I don't think I finished that up here. My domain would become so my original domain here was -1. It's my range actually. Y to 3, it becomes -1k to k3, or 3k. So that is how my range would change. Because it's asking, how does the range change? We use our scale factor to multiply the minimum and the maximum of our range and the minimum and the maximum of our domain for each. Cool? Cool.